Welcome back to the wonderful world of astronomy. This is Chapter 8, Formation of the Solar System. In this video, we'll look at explaining major features of the solar system. Our goals for learning in this video: what caused the orderly patterns of motion in our solar system? Why are there two major types of planets? Where did asteroids and comets come from? And how do we explain exceptions to the rules? First, I want you to think about the motion of the planets around the sun. And here you can see in the picture on the left that they are all going around in the same counterclockwise direction. Note also that that's the direction the sun is rotating on its axis. It's the direction that most of the planets are rotating on their axes. And then you can zoom in and see here the inner planets, and they're all doing the same thing. With the exception of Venus, which goes backwards, and Uranus, which is tilted on its side. Let's look at that outer picture, the picture that was on the left. Large bodies in the solar system have orderly motions. All planets have nearly circular orbits going in the same direction in nearly the same plane. Most large moons orbit their planets in the same direction, which is also the direction of the sun's rotation. And then we zoom in and we can see that with the inner planets as well. So the question is, how did it all come to be with these orderly patterns of motion? We're going to go back to the nebular theory that you were introduced to in the last video. The idea of the solar system collapsing from a large cloud of gas, that's the nebular theory. And so here we have a very large, thin cloud of gas, and by large I mean maybe several light years in extent. The original cloud is large and diffuse, that means just thin, not very dense, and its rotation is imperceptibly slow. The cloud begins to collapse through gravity. Now, as it collapses, conservation of angular momentum says that whatever slow rotation it had in the beginning, as it gets smaller and smaller, it will start to speed up. Rotation of a contracting cloud speeds up for the same reason a skater speeds up as she pulls in her arms. Now, as things are falling in, the farther they have to fall, remember, distance to fall is related to gravitational potential energy. So the things that fell in the farthest, they're going faster and faster. And all that energy that they had, when they get to the middle and they start colliding in the middle, becomes something, and it becomes thermal energy. So it starts to heat up in the center. And that center is what will eventually become the star. So now we have gravitationally, that's what these reddish arrows represent. Gravitationally, it's falling in. The blue arrows represent it's getting faster and faster, and it's flattening into a disk. Collisions between particles in the cloud cause it to flatten into a disk. So you can look at this picture on the left, and let's imagine these two particles. One, its trajectory is shown with the green, the other is shown with the red, so they've got some vertical components, and they will collide into each other, and their vertical components of their speed will tend to cancel out, so it flattens. Now that's just a depiction of two particular particles, but we're dealing with trillions upon trillions upon trillions of particles all colliding, so the net effect is that the cloud will flatten. The result is a spinning flattened disk with mass concentrated near the center and the temperature highest near the center. So that center is what we call a protostar, or the proto-sun if we're referring to our own solar system. That will eventually become the sun when it heats up enough to ignite nuclear fusion. The disk is where planets are going to form. So collisions between gas particles in a cloud gradually reduce the random motions. Collisions between gas particles also reduce up and down motions. And so the spinning cloud flattens as it shrinks. And this, again, it's a photo I've shown you before. It's a photo of out there in space, a hot center, and the disk that's forming. So this one day we think will be a star system with planets. And there's that familiar picture down to the right and another one up here to the left. Now you look at a picture like this and you notice, first of all, it's dark in the center, but that's because they have blackened it out. They've blocked out the star so the light from the star doesn't overwhelm the light from the relatively darker disk. You can see the disk. You can see a gap in the disk. In the picture down here to the right, you can see many gaps. Well, in this picture, you can see one clear gap, possibly created by an unseen planet. So observations of disks around other stars support the nebular hypothesis, or the nebular theory. This is a picture, the one up and to the left, of Hubble from Hubble Space Telescope. It shows a flattened spinning disk. And the gap that I pointed out, it says in the caption below, the gap in which material seems to have been cleared away, probably by a planet forming in the disk, which would have a gravitational attraction that would tend to sweep up material along its path. Now, this orange disk that I've shown you a few times, it's from an observatory called ALMA. You can read down below. It's called the Atacama Large Millimeter Submillimeter Array, just known as ALMA. Millimeter and submillimeter refers to the wavelengths that it looks at. The concentric gaps in the disk are almost certainly regions being cleared as planets form. The disk diameter is about 3 times that of Neptune's orbit around the sun. So remember that Neptune orbits the sun at a distance of about 30 astronomical units, which means its diameter of its orbit around the sun is 60 astronomical units. And you can compare, here's a little bar, that's 50 astronomical units. So this bar here is showing the scale of almost the diameter of Neptune's orbit around the sun. The background image, it says, from Hubble shows the star-forming region, the stellar nursery in which the disk is located. Another disk seen edge-on with jets extending outward appears at the lower right, so right there. Next question we can address is, why are there 2 major types of planets? Remember, there are terrestrial planets, Mercury, Venus, Earth, Mars, and Jovian planets, Jupiter, Saturn, Uranus, and Neptune. I want you to remember from chapter 7 some main differences between these 2 types of planets. So let's look down this table. This is just mentioning 4 of them. The terrestrial planets are relatively small in mass and size. The Jovian planets are large in mass and size. The terrestrials are the 4 closest planets. The Jovians are the 4 farthest planets from the sun. The terrestrials are made of metal and rock primarily. The Jovian planets are made primarily of hydrogen, helium, and hydrogen compounds. The terrestrial planets have few, if any, moons and no rings, and the Jovian planets have rings and many moons. So to understand why there are these different types of planets and why the terrestrials formed close to the sun and the Jovians formed away from the sun, we have to have an understanding of what the solar nebula was made of. Back when it was just a cloud of gas, what did it consist of? And so there are 4 main categories of materials that I want you to know. The most prominent in the solar nebula was hydrogen and helium gas. In fact, you can see these squares show relative abundance by mass. The solar nebula, before there were planets, asteroids, comets, the sun, it was a cloud of gas, and it was 98% hydrogen helium gas. And in fact, that is the composition of our galaxy, 98% hydrogen and helium. Now, of much smaller abundance, but important in understanding how the planets formed, there were hydrogen compounds. Now, compounds are these more complex, they're still simple, but more complex than just the elements hydrogen, helium. And these were molecules, so water, methane, and ammonia, for example, compounds made of hydrogen among other elements. And that was 1.4% of the solar nebula. To a lesser extent are rocks and metals. And actually, for the purposes of this discussion, we can just group rocks and metals together. Although rocks were 0.4%, various minerals, metals 0.2%, and that's things like iron, nickel, and aluminum. But again, for purposes of this video, we can just lump rocks and metals in there together for a combined abundance of 0.6%. Now let's go over to the middle column. This is going to be very important here. These different categories of materials can condense at temperatures below what's given in this column. Now, condensing means turning from gas into a more rigid structure, so either liquid or solid. And you think when you have maybe a bottle or a cup of ice water on a hot day, and water starts to build on the outside of the cup or bottle. That's called condensation. So it's not that water leaked out from the inside of the bottle, but rather water vapor in the air is a gas, and when it comes into contact with the cold bottle or glass, that water vapor will turn into a liquid. So we say it's condensating. So we're looking at what temperatures these different materials will go from gas into either a liquid or a solid. And so most of the solar nebula, the hydrogen helium gas, 98% of it did not condense in the nebula. So it takes very, very cold temperatures, very close to absolute zero. So they just never got that cold to condense. Hydrogen compounds will condense at very, very cold temperatures, so 150 Kelvin. So we're going to, on the next slide, look at regions of the solar system where it was cold enough away from the sun to where hydrogen compounds did condense, and it became the material of planets. Now we go to rocks and metals, and those become solids at very, very high temperatures. In everyday life, you don't see liquid rocks because they are solids even at high temperatures, even pretty close to the sun, where Mercury is, for example. These things, they are already, they're solid close to the sun, they're solid far away from the sun. You have to get really close to the sun in order to have those be liquid or gas. Okay, so we'll keep these categories in mind. What I want you to remember, I'll show this this slide, or I'll show this diagram on the next slide, but I want you to remember hydrogen helium gas made up most of the solar nebula, followed by hydrogen compounds, and to the smallest extent, rocks and metals. All right, let's go to the next slide. All right, remember the disk that we said, the solar nebula, that it was collapsing and it flattened and it's a spinning disk. We've got our very hot center, and the closer to the center, this is where the sun is eventually going to be. It's not yet the sun. We call it the proto-sun, but it's very hot there at the center. And the farther away you are from the sun, or what's going to be the sun, the colder it gets. So there is this dividing line. We call it the frost line. Inside the frost line is where it's too hot for hydrogen compounds to form into ices. So the only thing that is going to be solid inside the frost line is just rocks and metals. Outside of the frost line, it's cold enough for ices to form, meaning hydrogen compounds, they can solidify. So inside the frost line, you've got rocks and metals solidifying. Outside of the frost line, you've got rocks and metals and additionally hydrogen compounds solidifying. And by the way, keep in mind the top category, what most of the nebula is made up of, hydrogen, helium gas, that stuff doesn't solidify anywhere in this picture. So now we think of the planets that formed. The planetesimals. It starts as little fragments, little flecks, and they collide into each other. And by something that is like what we call static cling, they start to stick to each other. And eventually they start growing. and maybe get large enough to where gravitationally they start attracting to each other. Now, it was a very violent, cataclysmic place, the early solar system, with lots of these planetesimals. And so lots of times they would, as they're building up, collide into each other and blow each other apart, but some did survive. Now, inside the frost line, remember that material, that solid material, is only rocks and minerals. And so those planetesimals that eventually grew and survived and didn't get blown apart by collisions, there were 4 of them. They just kept getting bigger and bigger, and they became Mercury, Venus, Earth, and Mars. Outside of the frost line, the same thing was going on, but there was more solid material to work with, because not only was there rocks and minerals, but there was also hydrogen compounds, so methane, water, ammonia, things like that. So having more material to deal with, those things became larger than the terrestrial planets. So what I've given you so far is a fairly accurate description of what you know the terrestrial planets to be, balls of rocks and minerals, but there's also atmospheres, and there's oceans on Earth. And so we still need to explain those. In the outer solar system, there is there are these gas planets. What we think happened was the planets early on in their formation were these large balls, these solid balls of rocks, minerals, and hydrogen compounds. But being large, they had enough gravitational attraction to attract large amounts of gas, because remember, there's still the hydrogen and helium gas in the solar nebula. So they attracted most of that. So essentially, all the hydrogen and helium that we think of on these gas giants, you can think of those as their atmospheres, just like Earth has an atmosphere. But we actually consider that hydrogen, helium not simply to be the planet's atmospheres, but rather we consider them just a part of the planet, just because that is the majority of the mass and size of these planets, the hydrogen, helium gas. So how did the terrestrial planets form? Small particles of rock and metal were present inside the frost line. Planetesimals of rock and metal built up as these particles collided. Gravity eventually assembled these planetesimals into terrestrial planets. This process is called accretion. So here we go. Many smaller objects collected into just a few larger ones. Early in the accretion process, here we have the sun, or the proto-sun at least, with many, many small objects. There are many relatively large planetesimals on crisscrossing orbits. As time passes, a few planetesimals grow larger by accreting smaller ones, while others shatter in collisions. Ultimately, only the largest planetesimals avoid shattering and grow into full-fledged planets. So there we have Mercury, Venus, Earth, and Mars. Not colored appropriately, but there they are. How did the Jovian planets form? Ice could also form small particles outside the frost line. Larger planetesimals and planets were able to form. Gravity of these larger planets was able to draw in surrounding hydrogen and helium gases. So here we have the sun and a spinning disk around a forming Jovian planet. And so this disk around, let's just call it Jupiter, just like the sun has a disk going around it where planets formed, it's believed that there could be a disk going around these larger Jovian planets, such as Jupiter, and that disk would eventually form into the moons of Jupiter. A combination of photons and the solar wind, which is outflowing matter from the sun, blew away the leftover gases. And now we look at the question, where did asteroids and comets come from? Or remember back a few slides ago, I showed you this picture, the accretion process, explaining how planets formed. Asteroids and comets are just leftovers from the accretion process. They're just objects that didn't quite become big enough to become planets. The asteroids, remember those are rocks, they formed inside the frost line. Remember the frost line inside it is where rocks and minerals could condense. And outside the frost line is where comets formed. The early solar system was an environment of heavy bombardment, things slamming into each other. Leftover planetesimals bombarded other objects in the late stages of solar system formation. So then we look at, where did Earth's water come from? Where did the atmosphere of Earth, Venus, Mars, where did these atmospheres come from? And the main answer to that is, we think, from comets. And so you think the Jovian planets gathered their large gaseousness, their gas from hydrogen and helium in the solar nebula. But where did this gaseous oxygen and nitrogen, carbon dioxide, all these things that are in the atmospheres of the terrestrial planets, where did it come from? And we think from comets. And so comets were icy planetesimals. I put a question mark there because we really don't know where these oceans came from. It's been speculated that it was large comet bombardment that hit onto the Earth and gave us the oceans and the atmosphere. How do we explain exceptions to the rules? A Mars-sized planetesimal in this picture crashes into the young Earth, shattering both the planetesimal and our planet. This is the current theory of what formed our moon. Hours later, our planet is completely molten and rotating very rapidly. Debris splashed out from Earth's outer layers is now in Earth's orbit. Some debris rains back down on Earth, while some will gradually accrete to become the moon. Less than 1,000 years later, the moon's accretion is rapidly nearing its end, and relatively little debris still remains in Earth orbit. So that's how we think the moon formed, that something very large smashed into Earth, blew out a large chunk of its crust, and that debris eventually accreted and went into orbit and became our moon. Some planets have unusual moons, and Mars has two very oddly shaped small moons. And it's thought that these two moons of Mars are basically asteroids that were captured by Mars, small planetesimals that Mars's gravity captured into its orbit. Neptune has a strangely moving moon. It's one of the largest moons in the solar system. It's called Triton, and please don't mistake it with Saturn's largest moon called Titan. This is Triton, and the weird thing about it is that it orbits around its planet backwards. Remember I said that most of the planets rotate in the same direction and they go around the sun in that same direction. It's the same direction the sun rotates, and most large moons, this is the one exception, go around their planet in that same direction. Triton is the exception, and Triton is a very, very large ball of ice, similar to Pluto. And it's believed that Triton was, think of it as a very large comet that was captured at some point by Neptune's gravity. It just happened to be going in this direction when it got captured by the gravity. And so that's our current explanation of why Triton goes around its planet backwards. Here's a size comparison. As you think about Triton, one of the largest moons in the solar system, or you can think of it as a very large captured comet. There's a size comparison between Neptune, Earth, and Triton. A good theory of the solar system's formation should explain odd rotations. So it is thought that giant impacts maybe can explain the different rotation axes of some of the planets, notably Uranus, as you see here. Notice even its rings are on their side, and Venus, which is upside down. As we conclude, Here's a thought question. Which of these facts is not explained by the nebular theory? And the first is there are two main types of planets, terrestrial and Jovian. The second is planets orbit in the same direction and plane. The third is existence of asteroids and comets. And the fourth is the number of planets of each type, for terrestrial and for Jovian. And as you think through this part 2 video, I've actually given explanations A, B, and C. What was not explained is the number of planets of each type, that there are 4 terrestrials and 4 Jovians. According to the nebular theory, there could have been any number of terrestrials and Jovians. There just happened to be 4 and 4. And that's it for part 2, explaining major features of the solar system. Have a great day.